In the early 1950s, NASA was secretly working to design the first intercontinental ballistic missiles. The main issue was designing a warhead that could survive the intense heat of re-entry. This video is from the inside of the Orion capsule, where you can see the hot ionized gas that forms on the outside of the space capsule as it moves through Earth's atmosphere. When NASA shifted its focus to manned spaceflight, the re-entry problem assumed even greater importance. Harvey Allen, an aerodynamicist at Ames Research Center, hypothesized that a blunt body would provide the solution to the re-entry problem. NASA's Langley Research Center then conducted wind tunnel tests using blunt and sharp bodies. These tests clearly showed the difference in the shock wave profiles that formed around the capsules. Why do differences in shock profiles matter? Well, we'll take a look at that using simulations in Fluent. Two body shapes were studied in the Fluent simulations. The blunt body had a wedge angle of 55 degrees, while the sharp body had a wedge angle of 15 degrees. The wedges were subjected to Mach 3 flow with the following boundary conditions. This diagram displays the boundary conditions applied to the domain. In order to decrease computation time, symmetry was assumed at the midline of the wedge. The working fluid was assumed to be inviscid and an ideal gas. Fluent's compressible flow solver was used, and far-field conditions were set to 300 degrees Kelvin, and the gauge pressure was set to 101 kilopascals. The sharp body shown here has a thin shock profile that sits close to the surface of the body. Now, moving to the blunt body, we see that there is a dramatic difference between the shock profile developed by the sharp and blunt bodies. The blunt body develops a thick shock wave that sits in front of the body surface. So how does the blunt body solve the re-entry heating problem? The thick shock wave developed by the blunt body effectively creates a layer of insulating air, keeping surface temperatures lower compared to the sharp body. Right now we are looking at the blunt body, and we can see that the maximum temperature on the surface of the wedge is 836 degrees Kelvin. Moving to the sharp body, we see that the maximum surface temperature is 976 degrees Kelvin, which is higher than the temperature experienced by the blunt body. As speeds increase past Mach 3, the temperature difference becomes even more pronounced. All space capsules, including new capsules developed by SpaceX and NASA, have used a blunt body shape thanks to the ingenuity of a few engineers in the 1950s. The utility of computational fluid dynamics is also apparent here, as it took a few hours of simulation work by a single person to solve what was a very difficult problem in the past.